mathematics professor was giving a tour of the university to some new students. When he got to the cafeteria, he said with a flourish, "And this is our binomial cafeteria." One of the students asked, "Is it called that because there's so many choices?" To which the professor replied, "No, it's because you should buy no meal here." Get it? And we are starting our unit or our lesson on binomial distribution. So first of all, we're going to kind of revisit the way we did the problems the old-fashioned way with like the trees and everything. So say 30% of M&Ms are covered in speckles, like an Easter package, and mixed randomly with normal candies. You buy a bag and remove candies one at a time looking for speckles. What is the probability that one of the first three candies is speckled? So I could figure out, okay, what's the probability the first speckled one is the third candy? So it's going to be the last one I pull of the three. Well, the probability the first two are not speckled is 0.7, right? And so I'm going to 0.7 for each one. So it's 0.7 times 0.7 times 0.3, because the last one's speckled, and it's 0.147. So if I were to draw the tree, you'll see that there's more than one way to draw a speckled candy. The one I showed, the yellow one, is the one I calculated here. But I could have gotten not speckled, speckled, and then not speckled, or speckled, not speckled, and not speckled. So those are the three different ways that I could draw one speckled candy. All right, so I'll just take this answer up here and multiply it by 3 because there are three different ways. And if I multiply them out, I'm going to get that each time, right? So I multiply it by 3 and I get 0.441. Since each outcome is independent, in other words, we don't think the next candy's influenced that the first one's speckled, then each of the paths have the same probability, and we call these Bernoulli trials. So we're going to flip a coin 4 times, and what's the probability of getting 2 heads? Well, one way you could do it is you could do heads, heads, then tails, then tails. Now, the math can be a little confusing on this one because all the probabilities are 0.5. Probability for heads is 0.5 on one flip. Same thing for tails. So the probability of getting 2 heads first is 0.5 times 0.5. And the probability of getting 2 tails second is also 0.5 times 0.5. So I multiply it out and I get 0.0625. But what is the probability then that I'm going to get 2 heads? This is only one way of getting 2 heads. If I really wanted to find out how many different ways there are to get 2 heads, I could use the whole tree, right? So the one I drew, or the math I showed here, is for this path. Heads, heads, tails, tails. But how many other paths are there that give me 2 heads and 2 tails? Well, there are actually 6, all right? So I can take that 0.0625, that's on each one of these branches, and I will multiply it by 6 and get 0.375. All right, so if we're doing these problems where we have this probability of success and failure, I could draw a tree every time. But what if I have, and we'll be looking at a question of like a 10-question test, and it's multiple choice, and you can get the answer right or wrong. Do you really want to draw a tree for that? I can tell you right now that you would have 1,024 branches on the end of that tree, and that would be a lot of work. So is there a faster method? Well, let's picture the flips as flips A, B, C, and D. Kind of like you'd say question 1, 2, 3, and 4. How many ways can we choose which flips? So we're going to choose 2 of them out of the 4 total to have heads. Well, I could do, and here they are, A, then B, A, then C, A, then D, then B, then A, B, then C, B, then D, C, then A, C, then B, C, then D, and so forth. Does the order, though, actually matter when I pick the flips? No, we've got some redundancies. So A, then B is the same as B, then A. C, then A is already counted, as is C, then D, and all the ones that start with D. So I've taken out all the redundancies. Well, what kind of problem is this? It's actually a combination because order doesn't matter. Remember, we had the lesson where we taught you combinations. So if we did 4 choose 2, that would actually give us the number 6 as well. And that's way faster than drawing out a tree and figuring out how many branches give you the same thing. And this shortcut version is called the binomial model. The probability of X successes in N trials is, first of all, the combination. We have N to choose from, and you're picking X. Then you take the probability of success on one trial, that's P, and you raise that to how many successes you have. Then you take the probability of failure, which is 1 minus P. Some people use Q. And you raise that to whatever's left over for however many failures you're supposed to have. So this kind of looks like the multiplication we were doing out for the speckled M&Ms and for the heads and tails. And then this is the part where we counted the number of paths. So when can we use this? Well, we are only dealing with 2 outcomes, success and failure. And success and failure can look like different things. In our first example, success was getting a speckled M&M. Failure was not getting a speckled M&M. There have to be a fixed number of trials. In our first example, we were flipping a coin. We were drawing M&Ms 3 times, right? And I forgot how many times we flipped the coin. I think, it was 4 times we flipped the coin. So we were trying something a specified number of times. Probability of success has to be independent. The outcome of one trial does not affect the outcome of another trial. If you're sampling without replacement, sometimes it's okay, but you have to make sure the sample size is less than 10% of the population. Where does that 10% come from? It's a rule that's given to us. There are mathematical derivations, but trust me, you don't want me to get into it. It can be rather complex. But pretty much all the statisticians, they got together and they calculated and said, well, if you stay under 10% of the whole thing, you're not changing the probabilities too much. For example, if I had, I'll show you some examples. So let's go ahead and look at M&Ms again. This time we're just going to look at color, all right? And the Cleveland, Ohio factory are supposed to have the following color distribution. Brown is 12.4%, red is 13.1%, yellow is 13.5%, green is 19.8%, orange is 20.5%, blue is 20.7%. So those are actual numbers. All right, so we give you a package. There are 55 M&Ms in the package. Don't ask me how, but I know. All right, now what you're going to do is count how many M&Ms of each color are in the bag. So can we use a binomial model for that? Well, the main issue here is that we have more than 2 outcomes. So we're counting brown and red and yellow and green and orange and blue. Well, I just need something and not something, and that would make it a lot easier. Is it a fixed number of trials? Well, a trial is pulling 1 M&M out of the bag, and there are only 55, so you can only do it 55 times. It's fixed. Is the probability independent? Yeah, because I don't know to begin with how many I got in my sample. My bag is a sample of M&Ms, all right? And there's this big production line. In theory, it could put all the M&Ms the same color in there, but the likelihood of that is very low, all right? So it's not like I run out of oranges as I'm going through the bag, because I don't know that. It's not about sampling the bag, it's about sampling the production line, and the bag is a sample. Hope that makes sense. And each bag, trust me, is less than 10% of how many M&Ms were produced on that production line. But even though we were okay on the fixed number of trials and independence, we couldn't do it because we had more than 2 outcomes. All right, so let's change up the question. You count how many M&Ms it takes until you get an orange M&M from your package. Well, you could say the 2 outcomes are orange and then not orange. But I don't know how many M&Ms we're going to have to draw, so it's not a fixed number of trials. Independence, that's still there, because the probability that an M&M is orange is 20.5%, all right? Because in the production line, 20.5% of them are orange. So each M&M has a 20.5% chance of being orange, all right? Can we use the binomial model? No, because the fixed number of trials is not met. All right, so let's just count how many are orange in the whole package. Do we still have two outcomes? Yes, orange and not orange. Is there a fixed number of trials? Well, it looks like we fixed that. N is now 55. Is the probability independent? Yes. It's for the same reason I said before. Every M&M that went into that sample had a 20.5% chance of being orange. All right. And the binomial model, can we use it? Absolutely. Once you know you can do a binomial model, make sure you have your N identified, which in this case is 55. P, make sure you have that identified, which is 0.205. Now, X is our random variable, and that would be the number of orange M&Ms, and it can take values anywhere from 0 to 55, because we could have a package and not have any orange M&Ms in it, or they could all be orange M&Ms. Are those likely? No. But it's not, in theory, impossible. It is improbable, highly unlikely, but not impossible. All right, let's look at one more example for models. You get a deck of 52 cards, like playing cards, with 13 hearts. You draw 5 cards without replacement and count how many hearts you get. Well, do we have two outcomes? Yeah, heart or not heart. Fixed number of trials. Looks good. We're drawing a card, and each card we draw is a trial, and we can say we're going to do 5 of them. So N is 5, it's fixed. Is the probability independent? Well, because I'm doing that without replacement, and I know this deck has exactly 13 hearts. So let's say the probability of drawing the first card a heart is 13 times 52, but what about the second one? Well, that depends on if you drew a heart the first time or not. If you did draw a heart, there's only 12 left out of 51 cards. If you didn't, then it's 13 out of 51 cards. So P is going to change ever so slightly. And so for that reason, we can't say it's a binomial model. So let's go ahead and create a distribution or look at a binomial model for an example here. We're taking a 5-question multiple choice quiz, but we haven't studied and do not know any of the answers. Each question has 4 choices with only 1 correct answer. We want to determine the probability of getting a certain number of questions correct. What is a trial and how many are there, which is N? So a trial is answering a question, all right? And how many times do we do that? We do that 5 times. All right. What is a successful outcome? Well, hopefully you're going to get the question right. And what's the probability you'll get it right? Well, if you haven't studied and you have no clue, then maybe you have only a 1 in 4 chance of getting it right, which is 0.25. All right. So the outcome is the right answer on one question, and the probability of that is 0.25. So what is the random variable X for us? Well, it's going to be the number of correct answers after 5 attempts. Okay. It's always the number of successes after N trials. And what are the possible values for our random variable X? X could be 0, 1, 2, 3, 4, or 5, because you can get, it's possible for you to get no answers correct, and it's possible for, but not probable, for you to get all 5 answers correct. So let's go ahead and calculate the probability of getting no questions correct. So I'm going to go ahead and write down that N and that P. Those are going to stay the same in our model. N is 5, P is 0.25. Now, X for this question is how many we're going to get right. And we said 0. So I'm going to bring down the formula, all right? And we did 5 choose 0 for combinations, and 0.25 is our P, X is 0, 1 minus 0.25 for our probability of failure, and we do 5 minus 0. So we're just filling in the formula. And we taught you how to do combinations already. So 5 choose 0, you're going to actually calculate that to be 1. All right. So when we simplify and calculate, we get 0.2373. So about 24% of the time, you're not going to get any of them right. All right. So should you feel really lucky if you get them all right? Or could you do that? So let's go ahead, and n is still 5, p is still 0.25, but now x is 5. So plugging into the formula, probability of getting 5 right, we have 5 questions to choose from, and we have to get them all. 0.25 to the 5th, and then 5 minus 5 is 0. So once I do that, I get this really crazy number here. So if you haven't seen numbers this small, how do I interpret that as an actual number? Well, this is scientific or exponential notation. And this -4 here isn't actually part of the number, and you're not supposed to subtract it. It means move the decimal 4 spaces to the left. All right. So I'm going to rewrite the number here. And here's a handy trick. Add that many zeros in front of it. All right. Then we move that decimal 4 places. It's always going to land in between the first 2 zeros. So our number is actually 0.0009. We could round it to 8. Or if I want to go to 4 decimal places, which would be the 10,000ths, I would round it to 10 right there. Okay. So let's go ahead and calculate the probability that one question is correct. So the only thing that changes from previous problems is x is now 1. Substituting into our formula and then cranking it out, there you go. Probability of getting 2 questions correct. Okay, and well, let me make sure you understand. So the ones there, that 4 is the 5 minus 1, and these numbers are pretty much staying the same. So here, the difference is 3, so that one's going to pop up. So we have 5, choose 2. We have how many successes? Remember, this is our probability of success. If we have 5 trials and 2 attempts, that means 2 successes, but that means we must have 3 failures. And there's your number. All right. Now we do 3 questions correct. So 5, choosing 3 out of 5 questions correct here. We want 3 successes and 2 failures. And there's our number. And then 4. Here we have 4 out of 5 are correct. So we got to choose 4 out of the 5. 0.25 to the 4th. So we want 4 successes and just 1 failure. And what we can do is we can actually fill in a distribution table. So I'm going to just take all these numbers and put them in the table. All right. And if I were to graph them, well, let me make sure my model's right. And the best way to do that is to add these all up. And guess what I get? 1.000. Now, if you get like 0.999, it's probably just a little rounding error in here. So don't worry too much if you're not exactly 1. And what does this distribution look like if I graph it? Well, here's the probability of getting no questions right, probability of getting 1 question right, probability of getting 2, 3, 4, or 5. Is 5 impossible? No, it's 0.1%, but it's highly unlikely. It's highly improbable. So the most common outcome is actually 1 answer is correct. All right. So, but could you get 0 correct? Yeah, that looks pretty probable right there, and you can look at the table. And you can get 2 or 3 correct pretty easily. 4, it's a little hard. So the probability of you passing this test, just guessing, not super high. All right. So a calculator can do this as well. So first of all, I'm going to show you on the TI-84, but plus I'm going to give you a nice alternative applet that you can use. So the probability of X successes in N trials looks like this function, binom PDF NPX. All right. So to get there, what you're going to do after turning on your calculator is pressing second distribution. See the little distribution above? It's above the vars button. And second is there. There's the vars. Then you're going to scroll down till you get to this one, A binom PDF. Then for N, just go put in the number of trials or attempts. P, put in your probability. And X is going to depend on your problem. It's how many successes you want. Then scroll to paste down here and press enter. So if you're filling out a whole table, you're going to have to go through and do this multiple times for each value of X. All right. And remember, it's the P, the probability distribution function. There is an alternative. So I created this little applet on Geotrip. Geotrip had most of functioning. I just took a piece of it. And you can get to it using this link here. And what it does is something amazing. It will actually create a distribution for you and a table of your distribution function. Right now, it's defaulting to 20 trials and p is 0.5. So let me go ahead and show you what you need to set. First of all, make sure the dropdown shows binomial. You can change it, and we'll be looking at other distributions using the same applet. All right, so make sure that's binomial. For n, make sure you put in the right number of trials. All right, so it's attempts or trials. And for p, put in the probability of success on one attempt. All right, it's not the answer probability that you're looking for. It's just for one try, what's the probability you'll get it right. And the graph in the table that you get will show the distribution. All right. So first of all, let's go ahead. You're taking a 10-question multiple choice test now. So harder. You got 5 answers each. Oh, so it's going to be a little harder to guess right. So we're going to go ahead and figure out all the values for x. So what's the least number of questions? Well, let me first write down n. N is 10, and p is 1 out of 5, or 0.20. So you're going to try 10 times to get a question right. And the probability of getting each individual question right is 0.20. How many questions could you get right? Well, you could get 0 right, or you could get all 10 right. So our distribution function is going to have 0 here all the way going through 10. That's why it's got set of odds. I kind of chopped it up for formatting. So I could use the calculator, which means I do probability of 0 is binom PDF of 10, 0.20, 0. All right, because that's your x. There's your n, there's your p, there's your x. And I get 0.1074, and I would just fill that in. And I could do it again for 1 and put that number in. And I could keep doing for all values of x, or I could check out the Geotrip applet. So let me go there. And so you can see here, this has one wonky part. So I clicked on the n, and it pushes it down. So you have to scroll down. Now I'm going to change that to 10. And then the probability, got to scroll down again, sorry, change that to 0.2. And I'm just going to move these arrows out of the way so that you don't have to see them. And you can see there's our whole function, and there is the whole table. So I can just basically copy these numbers into this table right here. All right, and then add in the graph. So I could just look at the graph of it and draw the distribution. Now, you do notice that on the table on Geotrip, it only goes to the 10,000th place, which is the 4th decimal place. And you got some zeros here. Are they actually 0? Well, the probability of getting 9 successes. So probability you take a multiple choice test and you get an A on it, just guessing, is 10, 0.20, 9. So the calculator is kind of handy for getting the more detailed number. You see this -6 here? So I'm going to have to move this over 6 places. And so this is what it actually is. It's not exactly 0, but it's close enough. So make sure you understand what place value you're dealing with, and make sure that if something's 0, you might want to double check it with the calculator if you have access.